Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to start a new topic of discussion which is on power divider and direction coupler. So this video, I'm going to discuss all the basic properties of power divider and also power coupler. So this will be the objective of this video. This will be the part 1 series discussion on power divider and direction coupler. So guys, if you're keen to know more about power divider and also direction coupler, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion hopefully soon, as this is my first series discussion on power divider and direction coupler. This is my email. If you have any question regards on this discussion, please drop me an email. If not, I strongly urge you guys to send me your question through the comment. Okay, so this is because I hardly check this email. So guys, if you want to have a faster response, ask me the question through the comment. Thank you. I also like to urge you guys to help this channel by like this video. For those who are new to this channel, please consider to subscribe to this channel and also turn on your notification bell. Thank you. Let's quickly understand what is actually a power divider. Power divider is also known as power splitter. Okay, so this diagram shows a power divider or power splitter. You can see that there will be one input, okay, which is P1. There will be two output, which is P2 and P3. So from here, you can see that the power from P1 is actually split into P2 and P3. So this is how it implies the name power divider or power splitter. Okay, so when power divider and power splitter, when they actually use in a reverse way, so it is actually known as power combiner. Okay, so this diagram here shows the power combiner. So now there will be two input, P2 and P3, and there will be only one output, which is P1. So from here, you can see that P2 and P3 will add together to be at the P1. So basically, this is how it actually got its name as a power combiner. So in short, P1 is equals to P2 plus P3. Okay, so all this, okay, including this direction coupler, which I'm going to describe on this video also, all these, they are basically all passive microwave component. Okay, passive means that they don't require any power to work on. They are so-called non-active component and is simply just passive microwave component. Okay, so they are mainly used for power division. Okay, as I mentioned earlier, they basically split the power or they combine the power in the field of radio technology. Let's take a close look on this power division. Okay, in power division, an input signal, okay, so this will be the input signal, is actually divided into two or more. So there can be more than two, okay, at least two. Probably I should put it this way, into two or more output signal of lesser power. Okay, so what does this lesser power means? Which means that P1 split the power into P2 and P3. So therefore, the summation of P2 and P3, okay, which means that P2 plus P3, okay, must be less than P1 because the source is from P1. So hence P2 plus P3 cannot be bigger than P1. Okay, so this is a simple definition and requirement for a power divider or a power splitter. Okay, so as for a power combiner, they actually accept two or more. So from this diagram is actually two, but you can imagine that there are actually more input signal. It's also called as power combiner. So over here, they basically combine all the power into one output port. So in short, over here again, P1, okay, for this case here, cannot be bigger than P2 and P3, which means that the summation of P2 and P3, okay, P1 cannot be greater than the summation of P2 and P3, as the source is actually all from this input port. So therefore, P1 cannot be greater than the sum of P2 and P3. Okay, so this is a very simple definition on power divider and also power combiner. Okay, so let's take a look on this divider for three-port network. Okay, so basically let's do some understanding a little bit more specifically on three-port network first. The coupler or divider may have three-port, four-port. Okay, so this page I will illustrate on three-port. Okay, it can be either three-port, four-port, or even more, like five-port, six-port, etc. Okay, three-port network takes the form of T-junction. Okay, so this diagram here shows the three-port network. Okay, you can also see that I basically draw this T. Okay, so it can be like a T-junction. Okay, you can see from here, this is first port, second port, and third port, and I have drawn this T here. So they basically take the form of T-junction. Okay, while four-port network can take the form of direction couple and also hybrid, which I will illustrate on the next page here. Let's quickly understand this power divider or power combiner. Okay, so this diagram is actually a power divider. Okay, however, you can imagine them as a power combiner. Okay, earlier on I have mentioned, let's say this is actually a power divider. So the input will be at port 1, the output will be at port 2 and port 3. You can see that the input power is split into P2 and P3. So therefore, it is known as power divider. As for combiner, okay, you can imagine again, this port 2 and port 3 will be the input port, and this port 1 will be the output port. So over here, P2 plus P3 actually will form at P1. So basically, this is known as power combiner. Okay, the notation and symbol is actually shown over here. It is quite common to have this 3 dB divider, okay, which means that P1 power is split evenly between P2 and P3. In short, P2 is equal to P1 over 2. P3 is equal to P1 over 2, which means that P1 power is evenly distributed into P2 and also P3. Okay, let's take a quick look on this here. Okay, the power divider is used for device with tight coupling. Okay, commonly, a power divider will provide half the input power at each of its output port, okay, which is known as a 3 dB divider, which I have illustrated earlier on. And typically, this is usually considered for a 3-port network. Okay, so basically, this diagram here actually shows a 3 dB divider. Okay, as it evenly split the power of P1 into P2 and P3. P2 will be equals to P1 over 2. P3 will be equals to P1 over 2. Okay, so this is a very simple discussion on a 3 dB divider. Okay, so this diagram here shows the direction couple, okay, for 4-port network. Okay, let's go through here. So this will be port 1, port 2, port 3, and port 4. Okay, so port 1 will be the input as illustrated here. So this will be the source, will be the input. Port 2 will be the transmit port, okay, which means that most of the power should be transmit from port 1 to port 2, as this will be the transmission port. Port 3 will be the couple port. Okay, so basically this will be the couple port. What does a couple port means? For example, okay, as I illustrated earlier on, most of the power should be transmitted from port 1 to port 2. Okay, for example, if I couple 10% of the power from port 1 to port 3, 10%, just 10%, then this port 3 will be able to indicate how much power is actually transmitted from port 1 to port 2. So basically, this is known as a couple port. As for port number 4 will be known as isolated port, okay, which means that technically no power should be able to reach this port over here. So therefore, this is known as isolation. And in order to do this, typically they will terminate with a load. So in short, this is where the source of power, they come over here. Majority of the power should reach port 2, but some of them will actually couple over to port 3. So this is actually known as couple port. And technically none of the power should be able to reach port 4. And this can be happen when we actually terminate port 4 with a load. So again, you can imagine, let's say the input will be at port 2. Most of the power should be reaching the port 1 for this case here. So most of the energy will be from port 2 to port 1. So you imagine this will become the couple port. Okay, so basically some of the power of port 2 will be coupled to port 4. Okay, for this case now, port 4 is known as a couple port. As for port 3 will be known as isolate port. Okay, basically you need to terminate them with a 50 ohm. Okay, so basically nothing supposed to be reached at port 3 when the input is actually at port 2. Okay, I hope this is quite clear. Okay, you can actually work this in reverse direction also. Okay, so this direction couple actually designed to split power equally between 2 ports is actually known as hybrid couple. Okay, so in short, okay, let's say this power is going to evenly split to port 3 and port 2, then this will be known as hybrid couple. So in short, P1 actually split. P2 will be equals to P1 over 2. P3 will be equals to P1 over 2. So in short, the power is so-called evenly split, and therefore this is known as hybrid couple. Okay, so this diagram is what I have mentioned earlier on. Okay, so basically this will be what it means by transmit or through port here. So most of the power technically will be transmit from port 1 to port 2. Okay, some will be coupled over to port 3. Okay, none supposed to reach at port number 4 here. So basically this diagram here so illustrate this direction couple for 4-port network. Okay, so there are also a lot of parameters to discuss regards on this direction couple. But in short, some of the common properties that is desired for all the direction couple. In short, we want the operation bandwidth to be as large as possible. Okay, when the bandwidth is large, okay, which means that this direction couple can work in a larger frequency because it has a larger bandwidth. So in short, this will be desired. Okay, so this is also desired. Basically, we want to have a very high directive, okay, which I'm going to describe on this video what is directive also. And we also need to have a good impedance match. Okay, without a good impedance match at all the ports, there will be a lot of losses. So hence, in order to achieve or minimize all the loss, we need to have a match load at all ports. Okay, while the rest of the port, they are basically terminated in a match load, we need to ensure that we will have a good impedance match at all other ports. So these are all the parameters that we are going to discuss for a direction couple. Here, I'm going to discuss what is actually a coupling factor, the equation of coupling factor, same for insertion loss, isolation, and directive. So I will discuss in detail what are all these for. S parameter, probably I need another video to describe the S parameter of a direction couple. I will quickly also mention what is amplitude balance and also phase balance. So firstly, I will discuss on these four in order to let you understand what are all these four S parameter. On the next video, I will quickly go through what is a amplitude balance and also the phase balance. Okay, so before I continue, I'd like to urge you guys, if you have learned something from this video, help me by pressing the like button. For those who are new and you learn something, again, please consider to subscribe to this channel and turn on your notification bell in order to receive more information from this channel. Once again, thank you so much. Let's continue to understand what is actually a coupling factor. Okay, so what is actually a coupling factor? Okay, so this equation here is used to describe a coupling factor. You can see that basically will be involve port 1 and port 3, as some of the power will be coupled over to this couple port. So basically this is what it means. Okay, so basically where P1 is the input power, so this will be the input power at port 1, and port 3 is the output port from the couple port. Remember I told you that some amount of energy, let's say, can be coupled over to port 3, and hence this is what we call a coupling factor. How much will be coupling from port 1 to port 3? As I mentioned earlier on, most of the time, most of the energy we prefer to send it through to port 2. However, in order to know how much power will be sending from port 1 to port 2, some can be actually coupled over to port 3. For example, let's say 10%. Then from here, I will be able to know how much power is actually sending from port 1 to port 2. So basically, this is the meaning of coupling factor. And basically, this will be the equation. Okay, as illustrated, P1 will be the input power, P3 will be the couple port. Okay, the coupling factor is the fundamental characteristics of a direction couple. Okay, so for a direction couple, typically we need to have this coupling factor. Okay, this coupling factor is a negative value. Okay, and typically they cannot exceed 0 dB for a passive device. Okay, because this is a passive device, okay, this coupling factor cannot exceed 0 dB. In practice, okay, it typically does not even more than -3 dB. Okay, as this limit will lead to a more power being output from the couple port than from the transmission port. Okay, so in short here, what it means here, okay, so most of the energy, like I mentioned earlier, should be going through to port 2, or at worst case, equal amount will be sent to port 2 and port 3. We will not want to send more power to port 3. As I illustrate, we prefer to send more of the power to port 2. So basically, this is what it means here. So if this thing is actually exceed 3 dB, then it will be like a reverse their role. So this is actually not desired. Okay, while it is a negative value, okay, the minus sign is often omit. Okay, so basically for coupling factor, although it's a minus sign, okay, you can see over here, I actually omit the minus sign. Okay, additionally, coupling is not constant, but it also vary with frequency. Okay, which means that this coupling factor is not a constant number. In fact, it will change with frequency. Okay, so I hope you have a better understanding what is actually a coupling factor. In short, how much power is actually coupled over to the couple port. So basically, this is a definition of coupling factor. Next, what is actually an insertion loss? Okay, insertion loss means that what will be the loss, okay, in between, let's say from port 1 to port 2, there will be some form of loss from port 1 to port 2. Okay, so the main line of this insertion loss, okay, from port 1 to port 2 is simply governed by this equation here. So this will be known as the insertion loss, how much power is lost. So in short, as I mentioned earlier on, this will be the source, this will be so-called our final destination where we want to send over the power. So it is always desired to have all the power to send from port 1 to port 2, but this is not possible for this direction couple. Firstly, there will be some form of loss. Okay, so some form of loss, for example, insertion loss in between port 1 to port 2. And you can also see that some of the power is also coupled over to the couple port. So this is also a loss when we actually consider at the port 2 here, as not all the power from port 1 actually reach the port 2. Okay, so basically in short, this is a very simple definition. What will be the insertion loss from port 1 to port 2? As I illustrate, most of the power should be able to send from port 1 to port 2, but whatever the loss, we classify them as insertion loss. Okay, part of this loss is due to some power going to the couple port. As I illustrate, okay, for this so-called direction couple, some of the power will actually couple over to the couple port. And basically, this is what we call a coupling loss, and in fact is governed by this equation here. Okay, so this will be the coupling loss. So how much power coupling from port 1 to port 3, okay, is governed by this equation here. Okay, the insertion loss of an ideal direction couple will consist solely of coupling loss. So in short, let's say this is an ideal direction couple, there will be no loss in between port 1 and port 2. The only loss will be the couple loss from so-called the loss from power couple from port 1 to port 3. So this will be the loss. So this is what you mean here. The insertion loss of an ideal couple will consist mainly on coupling loss. In a real direction couple, however, the insertion loss comprise a combination of coupling loss, dielectric loss, conductor loss, and VSWR loss. So basically, in short, this is almost not possible to have so-called zero insertion loss, which means that insertion loss equals to the coupling loss. So in short, okay, insertion loss is actually included the coupling loss, the dielectric loss, conductor loss, and also the VSWR loss. Let's move on, okay, to isolation loss. As I mentioned earlier on, isolation loss means that technically when this is the input power, none of the power is supposed to be reached at port 4, which is known as isolate port. Isolation of a direction couple can be defined as the difference in signal level in dB between the input port and the isolate port. Okay, when the two ports are terminated by match load. Okay, so in short over here, these two ports we will terminate by a match load. Okay, and then we can calculate what will be the isolation loss. So basically, in short, okay, I don't want to have any power to reach this isolate port. I also want to have some idea how much will be able to reach over here. So in short, in the ideal world, okay, there is almost not possible to have a complete zero power that reach this isolate port. Okay, next, okay, let's quickly understand what is a directive. Okay, the directive should be as high as possible, okay, especially at the design frequency. Okay, so this directive basically will be very high, and especially true when we actually design the frequency, okay, where the direction couple is actually working. Okay, so this directive is directly related to isolation. Okay, so therefore, this is actually represented by this formula here. Okay, so basically this will be on a directive loss here. Okay, so basically you can see that this will be a simple form to describe the directive here. Waveguide direction couple will have the best directive. Okay, so basically when we actually use this waveguide, okay, for a direction couple, they will have the best directive. Okay, directive is actually not directly measured and is actually calculated from the addition of the isolation and the negative coupling measurement. Okay, so basically this is the so-called directive. How you can actually calculate is not so-called not by measurement, you can only calculate. So this will be the directive is simply I41, okay, which I have mentioned earlier on, which is the isolation loss plus the coupling factor. So basically by summing these two, I will have the directive. Okay, if the positive definition of coupling is used, then the formula change slightly. You can see that basically the coupling factor become negative over here if we want to use a positive definition of coupling. Okay, so this will be under the discussion of directive. Okay, so next, okay, on the last slide for this video here, okay, I'm going to explain what is actually a amplitude balance. Okay, this terminology define the power difference in dB between the two port of a 3 dB hybrid. Okay, so basically in short, if you still remember, okay, for example, I said that power 1 is split evenly to power 2 and power 3. Okay, which means that this is a power splitter. Okay, power 1 at the port 1 actually at the input and port 2 and port 3 at the output. So port 1 power is split evenly between port 2 and port 3. Okay, so in an ideal hybrid circuit, okay, the difference should be 0 dB. Okay, which means that there should not be any difference between port 2 and port 3. They should be equals to P1 over 2 because port 1 power is split evenly to port 2 and port 3. So basically, this is what it means in an ideal hybrid circuit. Okay, so this number should be 0 dB. Okay, however, in a practical device, the amplitude balance is frequency depend and basically they will not be at 0 dB. Okay, so basically in short, okay, although we want to split the power evenly, okay, but in the real world, okay, so this is not possible. Okay, in the real world, we cannot achieve 0 dB. There will be some amplitude balance. So basically, this is the definition of amplitude balance. Let's go through the phase balance. The phase difference between the two output port of a hybrid couple should be either 0, 90 or 180 degree. Okay, remember these two waveform, basically they can be either 0 phase different, 90 degree phase different, or 180 degree phase different. Okay, basically all these depend on the type used. Okay, same as the amplitude balance. Okay, the phase difference is actually sensitive to input frequency, and typically we cannot have so-called exactly 0, exactly 90, or exactly 180. There will be some variable of few degree. For example, instead of 0, I can have 1 or minus 1 degree of difference. Same as for over here, instead of 90, let's say I have 91, 92 different, okay, or maybe 88 and 89 different, so it's still considered acceptable. So basically, all this is known as phase balance. Okay, so with this, I'd like to end my discussion. Please help to like and subscribe. Once again, thank you so much for your strong support. I hope to see you guys soon. Bye for now. Thank you.